So today we're going to start chapter 3. Today we're going to look specifically at 3.1, which is Statements and Quantifiers. Chapter 2 was all about logic, thinking about Venn diagrams and that kind of arguments, set theory specifically. And so we're going to shift gears in this section, but we're still thinking about logic. Okay, so this section is still very much based in logic, or this chapter. So to start with, a statement. A statement is a declarative sentence that is either true or false. And we'll do an example. I ate cereal for breakfast. So that's either true or it's false. There's a couple of things about this that make it that way. It's a statement that identifies who, so it's saying I, as in me. So if it just said he ate cereal for breakfast, well, who's he? Like, you wouldn't know who he is. Like, that wouldn't make sense. You couldn't decide if it was true or false. So it's specific. And then you look at it and you say, well, that's either true or it's false. And that's what you're looking for to decide if something is a statement. So some things that are not statements. Some things that are not statements are questions. Right? What did you eat for breakfast? That's not a statement. Commands. Eat your breakfast. It's not a statement. Okay, so those are the two big things aside from that caveat of maybe being unclear as to who it's referring to, that would create something that's not a statement. So there's a couple of examples here, and I'd like for you to write them down to do them first, and then we'll make sure everybody's on the same page. You're deciding whether each of these is a statement or is not a statement. Okay, so you're gonna write it down. Just write it down for the two, and then we'll make sure everybody's on the same page in clarifying which is which. All right, so what do you think on the first one? Yield to oncoming traffic. Statement or not a statement? It's not. What's wrong with it? Or what is it? It's a command. Yeah, it's a command. There's not a true falseness to it. It is actually a command. How about the second one? 1 gallon of milk weighs more than 4 pounds. Statement. That's a statement. Does anybody know if that's true or false? I feel like it's probably true. I mean, a gallon of milk is probably more than 4 pounds. I feel like it's more than some of the weights that I pick up when I'm at the gym or whatever, you know. I mean, not the heavy weights, but you know what I mean, the light ones. So I think it's probably true. But it's either true or it's false. All right, any questions on statements, clarifying whether something is or is not? Okay, so the next thing we're looking at is compound statements. So compound statements are formed by combining two or more statements. And we're going to combine them with objects called connectives. So this is a list of connectives. It's not an exhaustive list. It doesn't include every possible connective there are, but it's some of the common ones that we're going to see. And, or, not, but, and if then. The three that we will most commonly see used are and, or, and if then. The reality is that the one that says not and the one that says but usually mean and, but they're being a little more descriptive, right? Something like saying, today is Valentine's Day, but I don't have a Valentine. Well, it really just means and. Today is Valentine's Day, and I don't have a Valentine. So those phrases with the and the not often are just replacements for another one of those three words, and, or if, then. So we're going to do the same thing on these two examples that we did in the last two examples. I want you to read them, and I want you to decide if the statement is compound for 3 and 4. So what do you think? The first one says, if Tom is a politician, then Jack is a crook. Is that a compound statement? Yeah, it is. This one's compound. What we're looking for is we're looking for two statements. The first statement is Tom is a politician. The second statement is Jack is a crook. And this one is using the if-then connective. So an if-then connective has a piece of it usually at the beginning and a piece of it usually in the middle. Doesn't always look that way. We'll talk lots more about if-then statements later. But this is a common way for an if-then statement to show up. How about number 4? Tomorrow is Wednesday. It's not compound. It is a statement, though, right? It's a statement that for today, anyway, is false. But this one is not compound. So we're looking for pieces that we can break apart into two pieces of statements and some kind of a connective between them. Now, another one of the connectives used the phrase, or used the statement, oops, it was right up there. It said not. Not actually can be also interpreted by using something called a negation. It doesn't create a compound statement in this way, but it definitely does create the feature of something being the opposite of what you meant. So negations are the logical opposite of a statement. And I'm going to use an example that I already used. The example that I used first off was I ate cereal for breakfast. This is a pretty simple statement. And what I mean by that is that it doesn't actually contain like compound. It doesn't have two pieces to it. It doesn't have descriptives like I ate a lot for breakfast, or what we're going to use later is something called quantifiers. It doesn't have any of those, so you'll see that in a moment. It's a pretty simple statement. So when we're looking at this and we're creating negation, the negation for a statement like this is to simply include the word not in it. So I ate cereal for breakfast. I did not eat cereal for breakfast. So often negations are that simple. You're just putting the word not in the appropriate place so that it makes sense grammatically and you're good to go. But if a statement has quantifiers in it, it becomes more complicated. So quantifiers are these words all, each, every, no, some, and none. Some, there exists for at least one. So there's a bunch of different kind of quantifiers, and they specify sort of how strong a statement can be made. All of you are enrolled in Math 1033A. All. Right? Not some, not one, all. So those phrases where we have these distinguishing features as to like how many, it's almost like describing how many, are called quantifiers. There's two types of quantifiers. The first one, where it has the all, each, every, none, are called universal quantifiers. They apply to everyone or to no one. These are the statements that you make to your parents where they get all riled up and they say, I always do my homework. And they're like, really? Remember that one time when, right? Or I never raise my voice. Oh, really? Really, never? Okay, so those are the overarching statements that are generally false when we make them. Generally not true statements. But we have these others where they're far less, commanding, right? They don't encompass everything. So they use the word some, there exists for at least one, and these are called existential quantifiers. Existential quantifiers show up when it applies some of the time and not some of the time, generally, right? So they apply to some people and not to other people. I have examples where it is true and examples where it's not true, in a situation. And those are called existential quantifiers. They exist, but they're not true all the time. Existential quantifiers make it more difficult to create negations. And that's this sort of warning down here, is that you must be careful when you're forming negations with quantifiers. In particular, quantifiers create negations that change the quantifier. So if I have a quantifier that's the word all, like saying, I always make my bed. I always make my bed. What does it take for it to be false? Well, it really only takes one time for me not making my bed to make that a false statement, right? Just one time. So if I were negating the statement, I always make my bed, I would have to say, sometimes I don't make my bed. Or there exists one time when I didn't make my bed. Like, I don't have to change it to say I never. It's not I go from I always to I never, right? There's something in between, and it's the in between that changes the statement. So in particular, when we have these universal quantifiers, right, the first one listed here, all, each, every, no, none, and we're negating things, we're going to create an existential quantifier statement. And likewise, when I have an existential quantifier statement, and I want in the negation, I'm going to be creating a universal quantifier statement. They're going to go back and forth when I create my negations. So, I'll use the example I've got on my paper. Here's an example of a statement that has a quantifier in it. First, I'd like for you to tell me what's the quantifier in the statement, some books are longer than this book. What's the quantifier? Not what type is it, just what is it? It's the word some. The word some here is a quantifier. What type of quantifier is it? It's existential, right? Okay, so if you can identify what the quantifier is and what type, that gives you a really good start to actually creating the negation. What that means is that I need to trade that word some for either the word all or the word none. And often I can change it for either one. It's just what comes next that will make the decision of which one sort of sounds grammatically correct. So we're going to write down two negations for this. One that contains the word all and one that contains the word none, or we might need to change it to the word no if it's grammatically weird, okay? I think it is. I think we need to do the word no. All or no. So if I'm saying that some books are longer than this book, and I use the word all, what would be the opposite of that statement? All books are what? Nope, because that's just a stronger statement than the statement I already have. If some books are longer, and now all books are longer, I haven't negated anything. I've just made the statement stronger. So what would I have to say? What's the opposite of saying all books are longer?
This book is shorter.
No? Okay, so that's my other statement. I'll write that one down since you've said it. So one of my options is to say no books are longer than this book. This is one way to say it. And it's the most sort of comfortable way. It's the one that we think of as being more grammatically correct. But there is another option. The other option, so going from what Jay said, is that if he said all books are longer than this book, we're actually going to say all books are not longer than this book. I've changed it from existential to universal, and I've changed the statement about being longer to being not longer. We don't generally want to write the word shorter. You won't see anything in my math lab that'll allow you to do that either. And sometimes that's because, and in this case it would be true, being not longer could mean that they're equal in length. That's why we wouldn't want to change it to shorter. Okay, it's because it could be that they're equal in length. So both of these are actually quantifiers, but the one that is more natural, I think, is the one that Connor said, which is that no books are longer than this book. That's a little bit clearer when we read it than the other one. Don't you agree? It is. So there's often, start with trying to do both of them, and if one of them sort of fails, you try the other one, and it's probably the more natural approach. We can actually do negations as well with mathematical statements like an inequality. So this inequality says that we have x is greater than or equal to 5. And we want the negation of the inequality. It says do not use the slash symbol because what they're saying is they don't want you to just do this. Is not greater than or equal to, right? Like, okay, but what does that mean? That's what they're telling you not to do. So going backwards then to the directions, what is the opposite statement of x is greater than or equal to 5? Yeah, x is less than 5. And notice what's happened is not only the direction of the inequality changed, but one of them has an equal and the other one does not. They can't both have an equal, and they wouldn't both not have an equal as well. Right? So these two statements, if I just had these two, are not negations because it excludes the possibility of equal. Well, where's the equal to part? Which one does it fit in with? It has to be with one of them. The one that they gave us originally had the equal, so the one that we create will not. Okay, any questions on that? Okay, so you've got a chart if you've got the notes printed out, and the chart looks a lot like the one I've got on my screen here. Change my color to black. There's 3 types of connectives that we are going to sort of hone in on. Do you remember what they were? I mentioned them, I highlighted them. The 3 connectives that we're going to work with. I'll go back.
And, or, and if then.
And, or, and if then, yes. So we've got the connective, that's the word and, the connective, that's the word or, and then the if, then. And we talked about the fact that there are other connectives, but they really just end up falling into one of these categories. The English language creates lots of duplication. This is one of those areas. There's some symbols that are used when we create these statements. Do you remember when we were doing Venn diagrams and we had intersections and unions? Y'all remember that? The symbols are very much like the intersection and union symbols that they were for Venn diagrams, or for sets specifically. So when we're looking at the word and, when we did that inside of set theory, the word and meant intersection. Do you remember that? And intersection had that upside down U. Great. So this one's actually an upside down V. Sometimes people like to think of this as looking kind of like the A without the line through the middle. So and, it looks like an A. Or it looks like half of an N, like a capital N, as a reminder. Or was our language that we used with unions. Yeah? And the union symbol was what? It was a U. And here it's actually going to look like a V. Okay, so the direction of the operation or the symbol that we're using is the same as when we did unions and intersections. If then, that's something new. We didn't have that when we did set theory. It's actually an arrow. There's one more I want to put in here. It's not really a connective, but I left it out. So I think it needs to be included here because we haven't included it yet. It's the word not. I'm so sorry. I'll need to make my little chart bigger. But it's not really a connective, but this is where I should probably mention it. Not actually uses the symbol, tilde. Okay, each of these are types of statements. The first one is actually a statement that's called a conjunction. So an and statement is a conjunction. An or statement is called a disjunction. An if-then statement is called a conditional. And those are the actual ones that are the compound statements. A not statement is actually called the negation, which is what we looked at a moment ago. So negations are this tilde symbol. They are the not statements. So we see some symbols down here. We'll go back to the phrasing here in a little bit. It says we've got tilde P and tilde Q. Depending on when you printed this out, I've changed something. Did I change it on this one? Yeah. I changed this to actually match the next problem where it said she is a teenager, and I changed it to say Leah. And then the other one to say he is a lawyer, and it's Joe. So if you've got that, just mark that and put the names in so that we would have the same examples as your notes. So it tells us that we're going to write this compound statement in words, okay? And you see some tildes, right? Those are going to have the words not in them. You see the individual statements, and you see the connective between. That's a conjunction. So we're going to just go from left to right, just like we would read the statement in English. So this tilde is going to mean the word not. So we've got a tilde and the P is the statement what?
Leah is a teenager.
Leah is a teenager. So what's the negation of Leah is a teenager? Leah is not a teenager. So we end up getting the word not. So Leah is not a teenager. The connective, that upside down V, what word will replace that? And. And the second part says tilde Q. So what is the statement Q? Joe, I think it says Joe. Mine says Joe. Does yours say Tom?
It says Tom.
Fabulous. Change it to Joe. We're going to all work with Joe today. I maybe had made an adjustment. Y'all printed it out, and my adjustment was wrong. Oh, my goodness. We're going to do Joe. Sorry, Joe is a lawyer. All right, so what is the negation of Joe's a lawyer? Joe is not a lawyer. Any questions about that? So we're going to be working in this section on going between symbols and English. That's really what we're going to be going between. And the other example actually uses the same P and Q. That's what I was wanting it to be anyway when I made my adjustments. And we're giving a statement now, and we're going to turn it into the symbols. Okay? So this is just the opposite, the exact opposite of this problem. Symbols into statement, or words into symbols. So we have the statement, Leah is not a teenager, or Joe is a lawyer. How would I write Leah is not a teenager in symbols?
Not P.
Yeah, not, which is the tilde, P. That is the statement, Leah is not a teenager. Okay, so there's three pieces. How do I write the or? That's a V. And how about the statement, Joe is a lawyer?
Just Q.
It's just Q. Tilde P or Q. VQ. Any questions on those? Okay, so your homework in my math lab is going to look just like this, right? You're going to be going back and forth between the symbols that are being used. All right, so we had an example earlier on about milk, and the milk weighing more than 4 pounds, a gallon of milk more than 4 pounds, and I said, do we know if that's true or not, right? So that's something that if you didn't know it, you could look it up, right? All of you could have grabbed your phone out, computer out, something, you Google it, you can find out, and we would all be good to go. So we're going to take a look at a couple of pieces where they're things we've talked about, but we haven't talked about them for a couple of weeks. So they might not be on the tip of your mind, but we did talk about different types of numbers. Natural numbers, which were the counting numbers, like 1, 2, 3, 4, 5. Whole numbers, it included the 0 in there as well. Integers had positive and negatives with the whole numbers. Rationals are the fractions, any kind of ratios. And then irrational numbers are things like pi and e. Okay, so those were the pieces we talked about. So these are actually deciding whether the statement involving a quantifier is true or false. So as you're taking a look at problems like these inside of my math lab, it might not be a bad idea to go back to those diagrams that we did that specified the different number systems as a reference point. So this one says to decide if all irrational numbers are real numbers. And the diagram I drew in class, just as a reminder, looked like this. It was this big diagram, and it had rectangles inside of it, and I split it in half over here like this little piece. And I said that all of these were real numbers. These were the rational numbers, and these were the irrational numbers. Does everybody remember that diagram vaguely anyway? Good. This is what you would be thinking of when you're looking at this statement. Irrational numbers. Are irrational numbers real? So thinking about this picture, what do you think? True or false? It's true. We took the real number system and we broke them down into two types of numbers, and there are no ones of these two types of numbers that are sort of outside that number system. So this is a true statement. Whoops. All irrational numbers are real. The next statement talks about whole numbers and positive numbers. So inside of this diagram, we had some rectangles or squares, either way, set up. They were like concentric, kind of like the nesting dolls at Christmas time. And we talked about I'll use symbols since I'm out of space. These are the natural numbers. Those are the counting. These are my whole numbers. And then these were my integers. That's how I specified them. And then we had our rational numbers that actually included everything. So everything in the rational numbers, everything inside these boxes are also rational. Everything inside this box is also here, and they just lie inside of each other. So this one, number 10, another universal quantifier, each, right, means like all, every single one of them. Every whole number is positive. You think about your whole numbers. Is every whole number a positive number? I see some heads this way, and I see some heads this way. What do you think? We could take a vote. We're not going to, but what are your whole numbers? Somebody tell me.
Isn't it so unique? Not decimals?
Not decimals.
On the number line change.
Okay, well, everything's on the number line, so I don't think we want to think about it that way. It's the hash marks we usually put on the number line, which I think is what you mean. Can you list them? Somebody list me the whole numbers.
Can't it also go to negatives?
Well, that's a good question. Do whole numbers include the negatives? They don't. Integers do, but they don't. I do have something that's missing here. Zero is missing. Whole numbers do include the zero. So are all these numbers positive numbers? No. What fails? Huh?
3.
3's positive.
0.
0 fails, yeah. 0 is not positive. This is a false statement. And all it took for it to be false was one piece, right? Just one number. That's the way existential and universal quantifiers work, right? They go backwards and forward. So if I'm trying to create a statement that is the negation of something that says all or every, all I have to find is one place where it fails. And I did. 0. 0 is not positive. It's neither positive nor negative. But it's definitely not a positive number. So this statement would actually be a false statement. Any questions on that?